game of chance, a player spins a square spinner labelled 1, 2, 3, 4. The player wins the amount of money shown in the table alongside, depending on which number turns up or comes up. So if they spin a 1, they win $1. If they spin a 2, they win $2. If they spin a 3, they win 5, and if they spin a 4, they win $8. Determine the expected return for one spin of the spinner. So that just means how much do you expect your winnings to be if you spin the thing once, and that's going to be a mean. And then B, determine the expected gain of the player. If it costs $5 to play, when it says gain, now that could be positive or negative. If you have a negative gain, it means you're losing money. And C, would you recommend playing this game? So that's really going to, if you're likely to lose a lot of money playing it, then you probably wouldn't recommend it. But obviously there are charitable endeavours as well. So what we're going to do, we're going to have two variables here. So I'm going to have I could have a variable W for winnings. So let W be the random variable winnings. So what we need to do is expect this, so draw the table for this, and we're going to find the expected winnings. So we are going to have maybe a little w, and then a probability big W equals little w. We're going to put them in like this. So the possible winnings are not the numbers, they are the actual winnings. So it's could be 1, 2, 5 or 8. So then for the probabilities, let's just have a think about the spinner. It's told us that it is a square spinner labelled 1, 2, 3, 4. So I'm going to assume it looks like this. That's not a very good square. Probably looks something like that, maybe split like that. And you have 1, 2, 3, 4. I'm going to assume that it's nicely evenly distributed. You've got a pin in the middle and you spin it, which would give all of these outcomes equal probabilities of happening. So I'm going to assume that all of these probabilities are a quarter. So you've got a quarter chance for each one. 1/4. So then the expected winnings are going to be the sum of all the W times P, W equals W. So expected value of W's, expected winnings, equals the sum of all the W, little w's, times the probability W equals W, which is going to be 1 times a quarter plus 2 times a quarter plus 5 times a quarter plus 8 times a quarter. You can, for ease of calculation, I'd probably pull a quarter out as a factor, so equals 1/4 times 1 plus 2 plus 5 plus 8. So that is 8, 13, 14, 15, 16. So it's a 1/4 times 16, which equals 4. So that means expected winnings are $4. So not looking good for part B. So for part B, given that I'm getting used to this notation, if we say let X, so let big X be the random variable expected gain, or we'll just put gain, sorry, expected variable gain, which you can read as profit. So here, this was part A, by the way. Part B, it's just asking me for the expected gain. Well, if the expected winnings are 4 and I pay $5 to play the game, well, the expected winning is going to be income minus expenditure. So it's 4 minus 5. Actually write down what it is. So expected value of X equals 4. Expected income, expected returns, the winnings, minus the cost to play the game, minus 5. So that equals minus $1. Minus $1. So that is not looking too good. Part C. Would you recommend playing this game? Well, anybody who plays this game, they're expecting to lose $1. Obviously, on any given game, they might win, they might lose. But if they play this, say, 1,000 times, 10,000 times, 1,000,000 times, they would lose money overall, and it would. The more times they play the game, the amount they lose would converge to $1 times the number of times they played it. So literally just the number of times they played it. Negative. So I wouldn't recommend it. But I mean, having said that, if you're designing a game, then it'd be a bit silly to design a game that loses money from your point of view. So I don't think it's too outrageous that the game, over time, they've got an embedded profit in it.